We are looking at differentiation of trigonometric functions. Okay, so let's have a look at what a sine graph looks like. Okay, if I was looking at a sine graph, looking at the graph y equals sine x, we all should know by now, ladies, gentlemen, boys, that sine graph starts at 0, goes up to 1, goes down to -1 at, let's use pi and 2 pi, pi over 2, 3 pi over 2. I know my graph isn't perfect, but it does up, down, ooh, down, up. Let's put pi to here. All right, okay. So that is what a sine graph roughly looks like. We all agree? Okay. If I am differentiating, if I want to know if y equals sine x and I want to know dy by dx, I need to consider the fact that dy by dx is the gradient. Okay, so the gradient at the top here is what? 0. So if I was looking at my gradient function, it would be down here at 0. My gradient here is also what? 0. Okay, because they're both flat points, it's the turning points. So we've got these 2 points here, which will be 0. At 0, the gradient of this curve is actually just 1. Okay, the gradient of a sine graph at 0 is 1. When it crosses pi, it's at -1. It's going downwards. Oh, wow. And when it's at 2 pi, it's back up at 1. So what you end up with is what? Cos graph. So the differentiation of sine x is cos x. Okay? If I was to then just say, if I've got y equals cos x, which I've already drawn, so I'm not going to draw it again, what is dy by dx? Let's choose a better colour than that, blue maybe. Dy by dx. Okay, so again, let's consider. What's the gradient at 0? What would the gradient up at the top here be? Sorry? 0. The gradient at 0 is 0. Okay, what would the gradient as it's going down be? Is it going to be positive or negative? Negative, and it gets to here and it approaches -1. So it's going to be down at -1. Okay, as it goes along this part, it's still negative, but it's getting less towards what? 0. Okay, then it's going to go up, so it's going to get positive until it's towards +1. And then it's going to go, it's still positive gradient, but it's going to reduce until it gets towards 0 again. So it's going to go down to here. So this is what the gradient of cos x looks like, the blue line. So, what does that remind you of? It's negative sine x. Sine x just flipped in the x-axis. So dy by dx, when y is cos x, is minus sine x. So sine differentiates to cos, but cos differentiates to minus sine. Minus sine x. Okay? And there's a proof here of why that is the case using basically the double angle formulas. So if you look at the page 95, I don't know if you've seen that before, but that is differentiation from first principles. Differentiation is finding the gradient. Okay? And whenever you find a gradient of a curve, what you say is, you know a point which is x, and the value at that point is fx. Okay? Because it's whatever the y value is when you put it into a function. To find the gradient, you're going to do rise over run. So you take a run of a certain value and a rise of a certain value, which it won't be to this line, it will be the tangent at that point to that curve. But if you take a point from the actual function, what we can do is take it so that's infinitely close to the point, and that approaches differentiation. That's why you see limits written on here. But if you call the difference between x to the next value, delta x, what we can say is the value on the function is x plus delta x, and then the function of x plus delta x. Okay? Which means that this is our y2, this is our y1, this is our x2 and our x1, so we do y2 minus y1 over x2 minus x1, which is what they've got written in the book there. Okay? Your basic understanding of how do you find the gradient at a point. Okay? The key thing is, though, with that delta x, they start to consider what happens to delta x as delta x becomes closer and closer towards 0. Okay? They apply limits to it. So let's actually use the y equals sine x thing as a thing. And this is kind of not needed for you, but it's interesting. So if you've got f of x plus delta x minus f of x all over x plus delta x minus x, and you say that the function you are looking at is specifically sine x, what you end up with is sine x plus delta x minus sine x all over x plus delta x minus x, which actually just becomes delta x. Okay? So, sine x plus delta x is a double angle formula. Sorry, not double. Compound angle formula. So you say sine x cos delta x minus sine delta x cos x minus sine x all over delta x. Okay? And as delta x approaches 0, okay, sine x cos delta x. Well, what's cos 0? If delta x is getting close to 0, what's cos 0? 1. So you just end up... Yeah, so you just end up with sine x minus as sine delta x, so sine 0, what's sine 0? 0. Oh yeah, plus, doesn't matter. Yeah, thank you. Plus. So yeah, sine delta x, as delta x approaches 0, sine x approaches 1. So that just leaves us with cos x minus sine x. Okay? The difficulty is that delta x is approaching 0, which means that you get divided by 0, but basically what you're left with on top is just minus cos x. Or plus cos x, sorry. Because the cos delta x becomes... hang on, what have I done? Hang on, sine 0 is 0, right? Yeah. Yeah, so cos x goes away, doesn't it? Hang on. Oh, right, sorry. They say as sine delta x approaches 0, it approaches delta x. So you end up with delta x over delta... there we go. Sorry. Because sine delta x is approaching delta x. If delta x is approaching 0, as sine of delta x approach... Sine x is 0, right? So we can say that sine delta x is also 0. Therefore, sine delta x is approaching delta x. Okay, if delta x is approaching 0 and sine delta x is approaching 0, then you can say that delta x is approaching sine delta x. Or sine delta x is approaching delta x. Which gets you this equation here, which leaves you with delta x cos x over delta x, which just leaves you with cos x. I only barely understand that, but I don't expect you to necessarily understand it. But basically, there's two proofs as to why. One's using a diagram, one's using like the diagram's not actually a good method, because for me to go oh, you know, at that point the gradient is 1. That's only because I know the gradient's 1 at -1, because I know what differentiates to. So I'm using my knowledge of what differentiates to prove it differentiates to it, which is not good mathematics, whereas the limits thing is the real thing. Okay, anyway, moving on. The other one you need to know is, what does tan x differentiate to? And I'm not going to show that one, but differentiates to sec squared x. Okay. The key thing is as well, all the rules to do with functions inside the brackets, as you would probably expect, you differentiate whatever's inside and times by it like in chain rule, basically. So if you look at the questions 2 sine x on example 4.9, page 96, 2 sine x will just go to 2 cos x because sine goes to cos. X cos x, product rule, okay? Whenever you got x times something, you're going to be using product rule now. You weren't here for. C, tan x over x squared. Simple ideas, but quotient rule, so you just got to throw quotient rule in there. And then the 3 plus 2 sine x to power 5, that's just using a bit of chain rule.
Oh, I didn't do quotient rule.
Yeah.
I did product rule, though, because that one was posted.
Yeah, so is quotient rule.
Really?
Yeah.
I didn't see that.
Okay. So, let's move on to the actual hard questions. Well, not the hard questions, but still easy. If y is equal to 2 sine 3x. Okay? So if y is equal to 2 sine 3x, what does dy by dx equal? Anyone know? No, okay. Well, basically, you take the differential of that, the 3x, you take the differential of 3x, which is 3, and you multiply by it. So it just becomes 3 times 2 cos 3x, because sine differentiates to cos, so this becomes 6 cos 3x. Okay, so wants to know is y equals sine ax plus b differentiates to a sine ax plus b, or cos ax plus b. Is that okay? Cool. Same for cos. If you've got y is equal to cos ax plus b, dy by dx is equal to minus a sine ax plus b. And lastly, the cos tan one, if y equals tan ax plus b, dy by dx is equal to a sec squared ax plus b. Is that alright? Cool. Very similar to things you've done before, like with the logarithms and the exponentials. It's always like differentiating the function that's attached to these particular things and then timesing by that differential. Okay? So in the other questions that we do, it's just applying the rules of product rule, quotient rule, and trigonometry. It's all just applying all the rules simultaneously in nasty looking fashions. There's nothing really to it other than getting good at using the rules. Okay? There's no special tricks. There's just learn the rules, put it into the rules, and don't mess up.
Thank you.
So, yeah, that's my motivation for today, innit? Don't mess up. Alright. Any questions before I stop it and you just do questions? No? Cool.